Excellent. So there have been some issues with the recordings of the webinar, so I'm trying something different tonight. I'm recording a Camtasia video over top of the Adobe Connect. So hopefully this will help us. If any of you tried to watch the recordings, my writing does not show up anymore, and it used to, but Southern New Hampshire is trying to get a hold of Adobe to figure out what the problem is. So in the meantime, we'll try to do workarounds. So because of that, normally I expect people to have watched the video, but it really does no good if you watch the one that has no writing on it. So I'll kind of go through the topics. No, it's not just you. I've been doing this for a couple years. This is actually the very last semester or last term that they're going to have webinars. But I've been doing this for a couple years, and yeah, all of a sudden my writing doesn't show up, and all my old ones where it did show up before now no longer shows up. So it's definitely an Adobe issue because I've not changed anything. So I'm sorry that that's happening. So tonight I want to look at really kind of intro to proof topics. So express the logical and conditional statements, do the truth tables, determine if arguments are valid or not using truth tables, and then look at some different proof strategies. So that's kind of the plan. And along the way, if you have any questions, just pop in any questions. So the first thing we need to know is, what's the difference between a statement and something else? So what is a statement? And it really is just a declarative sentence. It does not have to be a true sentence. It's just a declarative sentence. And then in terms of logic, we typically represent a statement with a P, Q, or R. And I don't know why we don't typically do more than 3, but we don't. So here are some kind of rules. So pick a color. So this piece right here is the conjunction. And I don't know why I even write that. It really just means and. So that's and. This one is the or. And little tilde is a not or negation. If you do any Google searches on this stuff, the symbol that is also used for not. So just know there are different symbols for different things sometimes. All right, so this column, the conjunction or and column, just says that the only way to get a true value using an and is if both values are true. So, and then all the rest are false. And then this next column is the negation of the and. So you just look at your previous column and you negate it. So you'd really just take the opposite. And then I was trying to show that these two columns are logically equivalent. And what I mean by that is they have the same truth table. So they're logically equivalent. If I can write this. Same truth table. Which means that those two things are logically equivalent. So not P and Q is the same as saying not P or not Q. So notice if you think about distributing that negative, so if you think about distributing this, when you do, it changes the sign. And this is De Morgan's law, if you've seen that before. That comes up in your homework. You're asked to write the conjunction, I forgot how it's phrased exactly, the and the or between two statements, and the negation of them. So just remember that when you're negating an and, when you distribute the negative, it switches, an and changes to an or. Any questions so far? Okay, good. I shouldn't say good, no questions. Again, I'm happy to have questions. It just makes me nervous when I don't see anyone typing. I suddenly think that you don't hear me anymore. So I just have to ask periodically. Okay. There's these things called quantifiers, and there's two quantifiers, the for all and there exists, and the for all is represented with that upside down A. So this statement in words means for all integers x, x squared is less than 10. So if I were to write out in words, for all integers x, x squared is less than 10. So that's what it means. So sometimes people get confused with what they mean and then the truth value. So two separate things. That's what it means. Now clearly that's not true. If x is 10, 10 squared is not less than 10. So the truth value is false. And again, to be false just means at some point it's false. To be true means you always have to be true. So there are some x values that make that true, but not all x values. So all of them do not work, so it's false. The next one, this backwards E, is there exists. So the statement there exists an integer x. So there exists an integer x such that x squared is less than 10. So what's the truth value on this one? Great, Jacob. All right, so it's true because there does exist one. 1 squared is less than 10. So good. All right, so we looked at the and, the or, and the negation. So this is a conditional or an implication, this P arrow Q. If you think about if-then statements, it's if P, then Q. That's the conditional statement. The only way for a conditional statement to be false is if your if part is true and your and your then part is false. So if you have if true then false is a false statement. And these last two pieces of that truth table are a little bit harder to understand. I just try to think of it as a rule. So if the if part is false, it doesn't matter what happens. Your whole statement is true, which again seems kind of weird. All right, so let's fill out this table. So this is an and. So what would my truth values be going down this table? So what would I have here? Awesome. So the only way for an and to be true is if they're both true. So if either one of them is false, the whole thing is false. Okay, good. And then now I'm going to have an implication. So this P implies the and. So I'm going to look at the first and third column. So in this first row, I have if true, then true. That's true. In the second one, I have if true, then false. Okay, that's where I get my false part from. Third row, I have false, false, which is true. And last one, I also have false, false. So because there are trues and falses, this is called a contingency because there are some trues and some false. If they were all true, it would be a tautology, and if it was all false, it's an absurdity. Okay. All right, so here's some examples of contrapositive and negation. The contrapositive is really important when we start writing proofs. So that, I guess I'll get that to them in a second. So just writing the negation of this, where P is today is Monday, Q is the grass is wet. The negation of P and Q is, we saw earlier, not P or not Q. And then in words that would mean today is not Monday, or the grass is not wet. So there's the negation in both symbols and in words. And number 2 says write the contrapositive. So we have the if today is Monday, that's P, then, so it's an if then, so P arrow Q. The contrapositive swaps the order and negates it. So not Q implies not P. And the really cool thing about contrapositive is these two are logically equivalent. So you can build a truth table for both of them and see that they are logically equivalent. I should say logically equal. So the contrapositive, again, swaps the order. So I'm going to have if the grass is not wet, then today is not Monday. All right, how are we doing so far? Still good? Awesome. I will just keep on going. Oh, I'm sorry. Where's here? Still always wet. Huh. I feel like we're always wet, but probably not as wet as you guys. Is anyone else seeing the video slow? Okay, so it's probably an internet connection if it's going slow. All right. So in the homework, Dave, you had that problem last week, right? And you said all of a sudden it caught up with you. So I don't, I've not heard that complaint before. But hopefully this time I'll have an actual recording for you to go back and see everything. I don't know. I made a PDF file with solutions to these problems I'm going over right now. And I sent them to all the instructors, so hopefully they will post them. I don't know if they have or not. I posted mine in the announcements if you're in my class. But I've also given them to the other instructors. So hopefully they're sharing the solutions to this webinar. Sorry, Dave. All right. So if my plumbing plan, all right. So what am I going to say? This example is similar to one on the homework that often causes problems. You are asked, is this argument valid? And I'm going to show you a kind of longer way to go about doing it, but it's a way that always works. Some students try to use modus ponens and modus tollens, which you can use. I'm not going to show you that way. I'm going to show you the truth table way, just from experience of what students seem to do well. So this first statement, if my plumbing plans do not meet the construction code, then I cannot build my house. Second is if I hire a licensed contractor, then my plumbing plans will meet the construction code. And then third, I hire a licensed contractor, and then the conclusion is I can build my house. So the first thing I want to do is just write all of these in terms of P, Qs, and Rs. So this must be an old one. So if I have P is plumbing plans do not meet construction code, would actually be not P. So let's start this out. P is plans meet code. And then Q is build house. And then R is hire, I'm going to say contractor. So now I want to write all of them in terms of symbols. So this first one, actually let me erase stuff first. So plumbing plans do not meet code, so I have not P, implies cannot build my house would be not Q. And if I hire licensed contractor, so that's an R, then plans will meet code, so R implies P. And then I hire a licensed contractor is R, and then I can build my house is Q. So that's each individual piece. Now to put them all together, you'd say not P implies not Q, and R implies P, and R implies Q. So all three of those pieces together, so the first three together, anded together, imply the conclusion. And this is what I'm going to build the truth table for. So before I erase, any questions on where that came from? Okay, I just had to write it down too because I want to go to another page to give me lots of space. Okay. Alright, so I'm just going to write this out again. We had not P implies not Q. And R implies Q. No, is it P? Is P. R implies P. And R. And that whole thing implies Q. Alright, so I have three variables, the P, Q, and R. So I need to have a column for P, Q, and R. And I have to make the table big enough to have all possible combinations of trues and falses among those. So I'm going to say, let's see, true, 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 and then I have 4 falses. And then I'm going to do the next one, Q. I'm going to alternate every 2. So I'll have true, true, false, false. And this is not the only way to do it. It's just the typical way that's done to arrange it this way. And then the R, I'll alternate everyone. So true, false, true, false. And then now I'm going to have a column. I'm going to do not P implies not Q. Notice that the contrapositive of this not P implies Q is Q implies P. So you swap the order and negate them. And it's easier for me to look at it this way if I look at Q implies P. Alright, so if Q implies P, I'm looking at, this column first, the Q, then the P. So true, true would be a true. The next one is a true. False then true is a true. False then true is a true. True then false is false. True, false is false. False, false is true. And again, part of that's just learning those tables, so having those rules for the conditional. The next one I'll do is R implies P. So now I'm looking at the third, then the first. So let's see. True, true is true. False, true is true. True, true is true. False, true is true. And then I have a false. Let me know if I mess up here, or if I'm going too fast. Now I'm going to do a column for, if I can fit all this in, not P implies not Q, so that's the fourth column, and R implies P, and R. So that is, which columns? The third column, fourth column, and fifth column. So all three of those together. If I'm going to AND all three of them together, I need all three of them to be true in order for the whole thing to be true. So here I have true, true, true. That's good. Then I don't. Then I do again. And then none of the others have all trues. And now I'm going to take this thing, I just don't want to write it again, implies Q. So it's basically it's this entire expression in my last column. If that entire expression, the entire column, is all trues, that means it's a tautology and the argument is true. If there are any falses anywhere in this last column, it is not a valid argument. So ultimately that's what I'm looking for. So in this last column, I am going to be looking at the most recent column with the second column. Alright, so that's where I get this from. Alright, so I have a true and then a true. So that would be a true. Then I have a false. I know if I start with a false, I have to be true, so I don't care what the other piece is. Then this third one is a true, implies false. I know that's a false. I can stop here because I have one false. The argument is not valid. All right, I typically have questions in there somewhere. You guys okay? Okay. All right, so Cynthia, if you so you feel like you need more time to maybe absorb some of it, and I think let me just write it in again. If you have questions for me at some point, if it's not coming. If the questions aren't coming now, feel free to ask me later, and I'll put my email in there. Yeah, it is a lot. Okay. Alright, so I'm going to stop sharing this and go back to the... Yes, Tyler, this example is on my PDF. And And again, the PDF doesn't have my words, but it has my writing, and I tried to color code things kind of nice, but better than nothing, I suppose. Okay. So now, kind of the last topic for this stuff is trying to prove things. So in this example, it says to prove if n is even, then n squared is even. So one type of proof is called a direct proof. And what a direct proof here would mean is you assume the if part is true. So you assume that n is even. And then our goal is to show n squared is even. So if I assume that n is even, that means that n can be written as 2 times some integer. And then I can just square both sides. So I get n squared equals 4k squared, which I can factor 2 out of. So I can rewrite that as 2 times 2k squared. And the reason I want to factor 2 out is to emphasize, to be even means you're 2 times something. So this is 2, I have 2 times something, so which is even. Therefore, n squared is even, and we're done. So direct proof is you start with your if part being true, and then work with it in some way to show that your then part is true. So let's try that same kind of process on a very similar question. It says prove if n squared is even, then n is even. So if I try the direct proof on this, I'm going to try, okay, n squared is even. Assume your first part. Well, if n squared is even, that means n squared is 2 times something, where k is some integer. But now if I want to get to n, I'd have to take the square root. So I'd get n is equal to the square root of 2k, but I can't factor a 2 out of that. So because I can't factor a 2 out, I can't say n is even. So I'm now stuck. So this one is very similar, but notice that the same method does not work at all. So let's think about how else we might approach it. So another method to, if that doesn't work, then you usually try the contrapositive. So the contrapositive of this statement, so think about n squared even, that's our p. N is even is the q. So the contrapositive is not q implies not p. So if n is not even, or if n is odd, then n squared is odd. So we know that the contrapositive is logically equivalent, so if I can prove the contrapositive is true, then my original statement is also true. So let's try the direct proof on the contrapositive. So if n is odd, that means n can be written as 2k plus 1. So basically an even plus 1, where k is an integer. And then if I square both sides, I get 2k plus 1 squared, and I FOIL that out, I get 4k squared plus 4k plus 1. And again, that right now I can't, is that odd or even? I'm not sure. But if I can factor it out in 2 times something plus 1, so let's try to factor a 2 out of that first piece. I'm left with 2k squared plus 2k, and I still have that plus 1 on the end. So now I am in that form of being odd. So I'm 2 times some number plus 1, which is odd. So therefore n squared is odd, and we are done. Any questions on using contrapositive to prove stuff? Okay. Well, the last kind of proof is really showing something's not true. So I think in the homework most of them say prove or disprove, so you really need to convince yourself whether or not it's true or not first. And you can usually do that by just looking at some examples. So this says prove or disprove. Well, let's take some values of n and test it out. So this n is a z plus, that means a positive integer. So some positive integers might be 1, 2, so on. So let's try some of those and see if it works. So if I have 1 plus 2 to the 1, is that greater than 3 to the 1? That's also asking, is 3 greater than 3? No. So I already disproved it. So to disprove, you only need one example. There's one example. I showed it didn't work, so it cannot work for all of them. Done. Trying to disprove stuff is a lot easier than trying to prove something. And so those are my examples. Do you have any other questions for me?